So as the last professor was leaving, he said, "Have a good class." And I said, "You too." So, how's all your days going? Is that good? So I'm really on point today is what I'm saying. I expect a very on-point lecture. Okay. So we're going to do a little bit of review and then cover the stuff that we didn't quite cover last time, then do some new stuff. So to remind you where we were at, we've been going through Grinnell, and Grinnell's been trying to convince us that the picture of science that most people, and probably most people who haven't thought about it before, have in their heads is just inadequate. It's just inadequate because it leaves out a whole bunch of what's he's talking about as the everyday practice of science, like the actual way in which scientific facts get developed. He calls it the linear model. The linear model is where scientific knowledge is just sort of added piecemeal, piece by piece by piece. We really don't go backwards. We don't have transformations. This process is objective in all of the senses that you care to talk about objectivity. It doesn't involve values. It doesn't involve really human judgment at all. It simply sort of builds up. We just sort of, with an open mind, we go to the world and we see some stuff and we write it down and then make a graph and then present it to the community, and that's how science is made. And we've been talking about this as the kind of science fair, the scientific method. When people talk about the scientific method, I inevitably get nervous because that shouldn't be a singular article there. It shouldn't be the scientific method. There are a bunch of scientific methods. There are a bunch of methods that are appropriate in different sciences, or accepted in different sciences. They don't all kind of look like this. They don't all follow this pattern. They don't all, and they certainly, this certainly is an inadequate picture of how scientists actually act. We talked last time about the kind of narrative structure of it. So the difference between a kind of the things that scientists write down in their notebooks or the actual activity in a lab, the difference between that and what appears in a journal article. So a journal article is a heavily cleaned up version of what happened in the lab, where you leave out the excitement and the confusion and the false starts and the tinkering and all of the stuff that kind of makes up the day-to-day activity of actually producing scientific knowledge. And they put it basically in this science fair style model, right? They make it seem as though they tell the story as though they knew all along not only what they were looking for, but what they would find. So they give us a really cleaned up narrative, and this narrative excludes sort of the value judgments, the unclarity, and all the complexity of actual practicing science. And it furthermore leaves off sort of just before the second cycle. So Grinnell's telling us about there's these two cycles of scientific practice. So the journal article captures, it's a sort of idealized version of this cycle where the individual scientist or a group of scientists is, of course, densely interacting with the world. They're trying to investigate parts of the world. It wouldn't be science if you're not like making observations at least. So of course, that part of the science fair method is right. You have a hypothesis, you make some observations. Hopefully the world pushes back and tells you whether your hypothesis is right or not. But the journal article leaves out this second half of the scientific process, which is the credibility cycle, where the individual scientist puts it into a journal article and then reports it to their community. And then the community responds in some way, and it's not simply everything that gets published in a journal article is uncritically accepted. And you don't want it to be that way. You don't want the scientific community to just sort of blindly accept any experimental result as indicative of what's going on in the real world. So there's a complex relationship not only between the individual scientists and the world, but also between the individual scientist and the research community that's sort of receiving their results, interpreting their results, trying to fit it into their broader worldview, trying to decide what parts of their previous thinking should be revised and what shouldn't. So the journal article stops more or less halfway through this process. And then, of course, when we're learning science, we learn it via textbooks, and the textbook cuts out all of this stuff. The textbook just tells you what's true. So textbook knowledge in science is the most reliable, the most accepted, the part that's already made it through the credibility process. So long after we see the credibility, long after the credibility process has done its sort of sifting and cleaning up and polishing of the results of this long, complicated process, what you get is the contents of a textbook. So people could be forgiven for, when they teach you science via textbooks, not being aware of this whole messy process that came before to produce this sort of nice, shiny textbook fact. Yeah? So that's what we've been talking about. If you accept all that, supposing that you've taken on board Grinnell's kind of complexification of what we're thinking of the scientific method or scientific methods, what he's done, and we'll see this kind of more clearly in the next couple of weeks when we talk about more in depth the discovery cycle and the credibility cycle, what he's done is kind of crack open the nice clean picture that's presented to us by the linear model and shown how there are choices being made here, and those choices are not mechanical. They're judgments, and sometimes they're value judgments. And that's not how science is advertised as a value-laden practice, right? That's not how it's sold to us. It's sold to us as objective in the sense of being at least value neutral. It's not sold to us as a product of a complex social negotiation in a community of people that you might not even be aware of. And that could potentially worry you that, it's not what we were sold, therefore maybe it's not worth as much as we were being sold it for. Like, you might worry that there's a potential for bias to creep into this process. And by bias, we might mean something like the distortion of objectivity. I mean, I think that's a very natural worry to have at this point. So if you accept what Grinnell's saying, that the process of coming up with scientific knowledge is much more complex than this sort of linear model makes it seem, well, now you might worry that there's the potential for bias here. There's a potential for the social process that's doing the credibility cycle and impinging on the individual scientist might distort the product of science, might produce products that are less true to the world in that sense of objectivity, or might produce products that are more laden with the values of the community than we might want. So Grinnell is certainly not a science skeptic. He's a scientist himself. He certainly doesn't want to convince us that science is all bunk and nonsense. But he does want us to take seriously this as a worry, and he's going to make the case that it's just not as crisp and clean as we might have thought. That the influence of values on science is real, and that it is potentially distorting, but that often it's not. So that very often the values and interests of scientists play a crucial role in developing scientific sort of facts, but that's not, when things are going well, that's not a problem. Right? That the fact that the scientists care about the results that they're dealing with doesn't make what they say untrue. It is just a fact about how this knowledge was generated. But of course, there is the potential for the bad kind of value-ladenness, the kind that actually distorts how the picture of the world that comes out of the scientific process. Yeah. So that's, I think, more or less where we got last time. Yeah. We talked a little bit, this is the last slide we got to. We talked a little bit about what was going on in the 1990s in the science studies industry. We talked a little bit about what I sort of laughingly called the science wars. So there was this, so the first type of the three types of umpire, the first type of umpire says, I call balls and strikes as they are. This is just kind of the ultra naive, like whatever I think is correct is correct. This is the linear model. This umpire corresponds to the linear model of science, where it's just like, no, we can just look at the world and see what's going on there, and there's nothing complicated about that process. There's just a fact of the matter, and I have access to it. So convincing us, Grinnell's attempts to convince us to abandon the linear model of science and take up a more complex model is his attempt to try to convince us that science is not like this first type of empire. It's not just a straightforward, clear, easy, objective, whatever I say is true is true. Now, we also talked about this third type of empire. What I call them is what they become. And the accusation was made, again, not by as many people as the hype makes it seem, but by some significant portion of people, especially in the humanities, mostly in the 1990s, where the fact that scientific knowledge is a social construct, it's a social product, right? It's a thing that comes out of a community guided by community standards. Those standards were not handed down to us from heaven carved into a stone tablet or anything, right? These are not rules that are just indisputably the correct rules. These are rules that we've come up with. They're the best we've got. We continuously improve them. So it was fairly clear, and I think there were strong arguments from the history and sociology of science that science is a social product. Scientific knowledge is a social product. And people started saying things like, well, science is claiming objectivity, but their output is social products. So there's this mismatch here. Science is claiming too much for itself. Scientists are claiming to have access to the really real world in a special way that's unlike any other way of generating knowledge. And they should be taken down a peg. They should be, this claim to authority that they're making should be rejected. So we'll talk a little bit more about this in the credibility, when we talk about the credibility cycle. Grinnell wants to reject this third type of umpire as well. So he thinks that science is not like this. I mean, there certainly are aspects of our lives that are like this. So when somebody says, I declare you man and wife, that speech act causes it to be true that those people are man and wife, right? Like sometimes you just make something a fact by doing a social act, by doing a linguistic act or something like that. So it's not like there's nothing that's like this. A lot of our sort of values and norms are like this. So like, my favorite example is like, blue is for boys and pink is for girls. There's nothing in nature that makes that so. That's not a fact about the universe. And it's not the case that every culture has thought that, and it's not the case that even Western culture has thought that all the time. So, like, it appears to me, even knowing that this is purely a social construct, I might say something is a purely social construct when there's nothing more to it than just, yeah, well, everybody agreed on that. Despite that fact, I nonetheless automatically, it seems so natural and easy and clear to me that pink is for girls and blue is for boys, right? Like that's just, my experience of that fact is as though it's a real natural fact, right? It's as though it's a fact of nature, but it's clearly not. We know that by just looking a little bit, digging a little bit into the history. So the claim being made by these critics, and they're possibly, maybe fairly or unfairly lumped together under the term the postmodernists. So postmodernists are people who are, so Jean Lyotard defined it as skepticism about meta-narratives. And a meta-narrative is supposed to be sort of an all-encompassing story about how reality works. So the postmodernists were skeptical about broadly anything that claimed to be a totalizing narrative, anything that claimed to be a complete story that into which all other stories could be fitted. They thought that was bad. So for example, religions often claim to be this way. So religions claim to have the story about reality, and that any other story that you can tell is either false or part of their story. Marxism looks like one of these things. So if you talk to a committed Marxist, kind of anything that you say, they can spin it into their class analysis. Yeah, it's all about the relationship between sort of the bourgeoisie and the working class, or something like that.
The Marxist dialectics is used to like model any two opposing ideas or forces.
Something like that. Yeah, yeah. So if you're, I mean, not everybody who thinks that the basic sort of social idea of like communism is full on that, but there certainly do exist people in the world who, for anything that you talk about, kind of my father was one of these, like any conversation would ultimately go back to Marxism. I'm like, we weren't talking about, but okay, you're back on your Marxism, okay. You know, so there are a number of these like meta-narratives, and science looked like it was aiming to be one of these things. Science looked like it was trying to be the story into which every other story could be fitted. You can call that view scientism, and there are, oh God, how do I conjugate this? Scientismists in the world. There are people that think that science is the one and only one way of gaining knowledge, that any knowledge that's legitimate is ultimately scientific knowledge, that there's nothing outside of science. So that's treating science as a kind of meta-narrative. And the postmodernists were very concerned about that tendency, and they were trying to combat it. Now, that more sophisticated story that I just told you isn't quite what this says, which is that the claims of science, so this is in a sort of extreme version of that. So the most extreme version of the science as social construct story that you could tell is something like, science is just a social practice, identical to any other social practice. So the claims generated by science are just, you know, like they're just like pink is for girls and blue is for boys. They're kind of arbitrary, except insofar as scientists are exercising social power and imposing them on people. So that's the most radical version of this. I'm not actually aware of anybody who thinks that or even thought it in the 90s. I don't know of anybody who defends that super extreme version, but when Grinnell says the postmodernists are wrong, that's what he's rejecting. He's rejecting the idea that just because science is a social practice, that it happens in communities and is governed by community norms, that it's just like, you know, the institution of marriage or the way money works or any of the other kind of pure social constructs that we talk about. So he thinks, Grinnell's going to make the case, that science is more like the second type of umpire. I call them as I see them, which is, I mean, it's a nice way of putting it, right? So the scientist is doing their level best to represent reality. Their goal is to say what's real, to say what's out there in the world, rather than trying to impose their viewpoint on the world. But there's a little bit of humility in here, isn't there? There's a little bit of acknowledgement that, you know, this is my best shot at it, but I might not have it exactly right. The way I see things, so I'm seeing it from a perspective, I'm doing my best to match my perspective to the world, but that's not it's not a gimme. It's not a completely transparent and trivial process. Neither is it unrelated to the world. Right? So there's something between these two types of umpires, and Grinnell's going to try to convince us that that's where science is, somewhere between those two extremes. Sorry. All right. Okay, so that's where we got to last time, yeah? Any thoughts on this so far? Yeah.
I think it'd be really interesting to take a postmodernist approach to structural building design.
What is it?
So right now, the roof above us is supported by steel and concrete. Theoretically, the person who designed this building could have said, well, there's no way to truly know what's true and what's false. Okay. So I can design this building however I want.
Right. The way I design buildings is the way they're designed, and therefore, yeah.
So like the faith that we put in science is like
Right.
put a lot of faith in it, because that science is then applied to engineering.
Right.
And that's why we can walk into this building without worrying that it's going to collapse.
Right, right. So I think it's a little unfair. So it's a little historically unfair to attribute, like, again, I don't know anybody who identified as a postmodernist who's just like, whatever you say goes. That's just whatever I say it is what the reality is. And there's nothing more to it. I don't know anybody who thinks that. Furthermore, I don't know any scientist who thinks that they know the absolute truth about reality. That there's no room for skepticism, that there's no room for error in the scientific process. So, so who, in some sense, every scientist has a little bit of the who knows, I don't know, who knows, you know, and this is why engineering is practiced the way it is practiced, with they over-engineer everything 10 times so they think, this is how strong it needs to be, now we're gonna make it 5 times stronger than that, because kind of who knows? That's how we actually practice engineering. So there is a little bit of the so let's distinguish skepticism from a kind of radical relativism. Skepticism, we could say, is just having less than 100% confidence in your claims. And I think we should all be less than 100% confident in our claims, because that's just arrogant and unjustified, right? I mean, we should be reasonably confident in our claims. Don't be at 0, that's also weird and unjustified. But everybody should be less than 100. 98, max, kind of thing. 99 maybe, but we also probably shouldn't be radical relativists in the sense that, so at least Grinnell thinks, we shouldn't be radical relativists in the sense that we just think whatever people think is fine. Use whatever equations you want. That's just any equation for deciding whether this bridge will stay up is as good as any other. And you picked out just the thing that Grinnell thinks establishes that case, which is the unbelievable success of technological implementations of science. I don't know how anybody could live in the 21st century Canada and be unaware of this or to reject it. I would love to hear your reason. If you think that, I would love to hear your reasons. Yeah.
Well,
you don't think that?
I don't think that.
Okay.
It might
Okay.
be useful to think about GPS systems,
Uh-huh.
where the way that it works is that you have 21 different satellites orbiting the planet,
Mm-hmm.
and they triangulate the position of your phone.
Mm-hmm.
That's why GPS works.
Right.
And if you consider all the science and engineering and math that went into that, and that if our understanding of the world was wrong, or if the scientific understanding of the world was wrong, then GPS wouldn't work. So the fact that it
Right.
does work implies that we have a pretty good understanding of how the world actually works.
We have certainly more than 0. That's that. We have to have something right? And if the theory of relativity, so if we tried to build satellites on the basis of Newtonian mechanics, they would fall out of the sky. It's only relativity. So the equations of Einsteinian relativity are required to make our satellites fly. They're required to calibrate our GPS, so the amount of time it takes for light to get from one place to another, the relative velocity of the satellites on the Earth, all of that's got to be factored in, or else GPS wouldn't work. So more than just we have nothing, we have more than nothing. We have the kind of predictions that we make just wouldn't work if we had science even from 100 years ago, 150 years ago. So I don't know. I don't know anybody who denies that stuff. So it's probably not worth getting too worked up about it. There are people who get really worked up about postmodernism, and I don't know who they're arguing with. I won't name any names, but yeah, they get really. It's called a straw man, and it's convenient to argue a straw man because there's nobody there to argue back with you. Yeah. Anyway, okay. So are we good on this stuff? The basic position here that Grinnell's trying to defend. I should mention, and I hope it's clear, you don't have to agree with any of this stuff that I'm saying to do well in this class. I'm presenting a point of view. I'm going to kind of argue for it, but I would love for you to disagree with me. That'd be fun. That's what we do in philosophy mostly, is disagree. So I invite your criticisms at any point of any of this stuff. That's an encouraged activity here. Yeah. Okay, yeah.
One more idea that might be interesting and useful is like, so you were talking about how there were previous models, or well, like the
Newtonian model, yep.
and how it got replaced when we figured out, quantum physics.
Yep, and relativity, yep.
And so like there are some postmodernists who criticize the scientific understand the world by saying that we just keep creating models and then replacing them. But it seems
which can you name any names?
I can't name.
Right. Okay. Yes, this is what I thought. Okay.
But it seems like what's going on is in models of increasing accuracy. So we keep replacing the models, but they are getting more increasingly accurate. I would argue.
Yeah. So here's a funny thing about the foundations of physics that doesn't get talked about a whole lot. We've got two big paradigms in physics right now, quantum mechanics and relativity. And the thing that we know for sure is that they can't both be true. They just can't both be true. They make completely incompatible predictions. They have basically different ontologies, so their basic picture of space and time are quite different. We know for sure that the two leading models in physics are incompatible with each other. It's one of the big projects in fundamental physics right now is trying to figure out something that would be compatible. So that's the promise of string theory or quantum field theory, the attempts to make these two big paradigms fit together. With Newton, at least it was internally consistent. So we went from an internally consistent picture of the world to it's very clear that it's inconsistent, that our two best theories about the universe, and they are fantastic theories, make no mistake, these are unbelievably good theories. Without relativity, satellites would fall out of the sky. The quantum mechanics, they predicted a particle that nobody had ever seen before, a kind of thing that nobody had ever seen before, the Higgs boson, in like the 70s. And they observed it, like 5 years ago? How old am I now? When the Large Hadron Collider observed the Higgs boson, they found it not just what they were expecting to find, exactly where they expected to find it, at the energy levels they expected to find it. And if that's not an unbelievably powerful theory, I don't know what is. But they can't both be true at the same time. And we're very confident, physicists are very confident about that. So don't tell me we're almost there, but we are getting more and more impressive results. Something's got to be fundamentally wrong about physics because they are two deeply incompatible theories. And the one they're proposing to replace it with, string theory, is called so speculative that it's not even a theory. So yeah. So progress is, and this is the difference between the linear model and the kind of more complex model, progress is not straightforward in the sciences. Yeah, it doesn't go in a straight line. It's not like we're 95% of the way there and it's just a matter of working out the details. That's what we know for sure, just by thinking about how quantum mechanics and relativity are related to each other. There's got to be some deep transformation in the fundamentals of physics before we can even believe that we're close to figuring something out here, or that we've got some sort of true theory. It's not like we're getting more and more true, we're getting more and more powerful. So, yeah. Okay. Yeah.
First I think that's super cool how the two B's in physics, but neither
they can't both be.
But that's a side point. But in I'm a biology major, and in my second year of university, one of our required courses is the methods of biological inquiries, which is basically how to do science kind of.
Very good.
And
what did they tell you there?
Yeah, well, it's just in the very first lecture, the first comment was basically science is only true until it's proven to be untrue, and then it was it's kind of like the joke you made in the first class. It's well, that's all you need to know now.
Right.
That's
right.
basically, and I think that's important to remember when learning stuff like this as well. Is that it's only true right now it might be true, but in the future you never know. That's
the difference between the first and second type of umpire. Mm-hmm. That's the difference between as they are and as I see them.
Right.
Yeah. Good. All right. Okay, so calling something as you see it is to include in the the calling it, that is the judgment about what's true, the fact that you're seeing it from a perspective. And this perspective is not just yours as an individual. In some sense, it belongs to a community. And we've been talking a lot about the kind of communal nature of science, the fact that it happens. The whole credibility cycle is a relationship between an individual scientist and the broader scientific community. So Grinnell says, in everyday practice, discovery begins in community. So when we're talking about things like Newtonian mechanics and quantum mechanics and relativity, those are all paradigms in fundamental physics. Most scientific communities have one of these things. There are some fringe cases that don't seem to have proper paradigms, but like most scientific communities, any kind of science that's mature, that's going, that's a sort of normal science, has a paradigm. And a paradigm is composed of things like shared values, interests, and assumptions. So what's an important observation? What's a good experiment? What's an interesting question? These are the kinds of things that are sort of built into a paradigm. And a paradigm is a really handy thing to have because in some sense, in the pre-scientific world, so if you think about something like alchemy, so before there was chemistry, there was alchemy. And alchemy was mostly a bunch of individuals with time on their hands who would hang out in their basements and do weird stuff. They would try out weird chemical experiments. They would sort of like just do stuff and see what happens. And the kind of secretive nature of alchemy was such that they all had many different, so there was sort of traditions of alchemy, but there's like 15 different traditions of alchemy. Whereas chemistry, there's just one chemistry. Yeah? So when you do an experiment in chemistry, you first learn the vocabulary and the assumptions and the methods of the discipline. And then you apply that vocabulary, the methods and the assumptions, and build your experiment on that basis. And then when you report back to the community of chemists, and they can read your thing and understand what the hell you're talking about. Whereas the chemists or the alchemists are mostly weird loners doing things kind of on their own. I mean, there was more kind of, there was like high alchemy and low alchemy. So there's the alchemists who were trying to generate what's called the Philosopher's Stone or the elixir of immortality. That was the kind of esoteric solo work that you wouldn't really tell other people how you did it because you didn't want them to come up with the elixir of immortality first. There was also kind of alchemy that was like, I read a medieval recipe for something to remove body hair. So that was the kind of thing that you could, and I think it worked too. With some really nasty chemicals in it. It would definitely have taken body hair off. So there was alchemy that really worked. There was a bunch of like stuff that you could cook up using the kind of what we would call the techniques of chemistry. But they all had different, especially for the more esoteric, the more kind of like high level stuff, they all had different language, different frameworks. They were secretive. And unsurprisingly, they did not make a lot of progress. Whereas if you have a paradigm, which is a set of shared language and shared methods and shared assumptions that you can try and see if they work and tell me whether they work, and I can try and see whether they work and tell you whether it works, right? We can all share this information. We can all share our techniques, compare whether it's working or not, all that stuff. Boy, you just zoom along compared to 100 people within a paradigm compared to 100 loner weirdos not talking to each other. That group that's talking to each other is going to outpace those 100 weirdos a million times over. Like, it's really incomparable how much more progress you make when everybody's talking the same language, using the same techniques. Yeah?
Humans function like a hive mind. So like...
That's a weird claim. Okay, go.
Okay. That ants behave. Basically, the ant colony is a brain. And then each individual ant is like a cell, a nerve cell inside of the brain. And so if you're looking at the way that a group of people operate, It's like each person is a brain cell, and then the group of people together is a brain.
I would modify that slightly. So I think there's something in there. I would modify it slightly and to say, when people are at our best, that's how we act. We often don't cooperate. It was pointed out to me a long time ago, it struck me very deeply, that one single human is a pathetic animal. One human raised in the wilderness without other human contact is basically a delicious snack for something that's actually good at hunting. We're just like, we don't have claws, we don't have sharp teeth, we're not that fast, we're not that strong, we're just like soft and delicious. Whereas 20 humans who can communicate and plan and teach each other stuff are the deadliest predator on the planet, by far. We took down mastodons. We extincted the mastodons, right? Because we were so good at hunting. Sorry, mastodons. I mean, we regret it now. It would be nice if they were still around, but like, we are incredibly powerful in groups and incredibly sad and useless alone. So when we're doing well, we act like a brain. When we're doing poorly, we don't. But notice this about paradigms. So what I just told you is that everybody's talking the same language, everybody's using the same techniques. That's deeply constraining as well. So to be raised in a paradigm as you're being educated as a scientist is kind of to be indoctrinated into one way of seeing things. Yeah? You don't get to just go and do physics any way you feel like. You don't. You don't get to just do biology in any way you please. You got to toe the line, right? This is the sacrifice that you make when you decide to participate in a, I don't know if you're aware, we live in a society. And when you live in a society, you got to kind of follow the rules. So I would compare, my favorite metaphor is to compare a paradigm to a set of binoculars. They let you see much farther and much clearer, but they restrict your view. They close down your field of vision. Yeah? Without the binoculars, you can see a much wider, broader picture, but you can't see as much. So this kind of trade-off that happens when you accept one framework for seeing things, one set of values, interests, and assumptions, you do restrict your view, but you can see a much, much farther. And history has shown us that the people who are willing to accept this restriction produce way more knowledge, like way more knowledge than people who are unwilling to accept it. Just compare the alchemists and the chemists. It's just there's no comparison between the two groups who produced more knowledge, right? When you try to act as a scientific community rather than as a loner scientist, and it gets truer and truer as history goes on. As the type of problems that science deals with becomes more complex, we become more and more interdependent. So what a paradigm does, I would suggest, is in some sense frame the world. A frame puts a box around something, yeah? It presents it in a kind of constrained way. A frame restricts your field of view. It says, only inside here. And we need that, not just as a matter of scientific process, but in literally all of our cognition. All of our thinking and reasoning needs some kind of constraint on it because there's just too much to consider. There's always way more possible observations to make, inferences to make about those observations. There's just way too much data available at all times to even begin to make a dent in considering it all. So we have to have something to focus us on just what's important. It's a very general fact about cognition, not just human cognition, but anything that thinks is going to need something to really narrow down our view. Imagine the set of all possible experiments, if you can. So I'm going to run an experiment on whether adding orange juice to boron on a Thursday affects the stock market. Now that's a bad experiment, right? That's not a good experiment. It's not a sensible thing to do. How do you know that?
Actually, it could be a good experiment.
It's a terrible experiment. No, it's a terrible experiment.
Listen. So you put the boron in the orange juice. You give the orange juice to someone who's trading on the stock market.
Right.
And because they've been poisoned by the boron, they're going to make terrible trading decisions.
Oh, God.
It'll have a significant effect on the stock market if that stock trader has access to a large enough trading account.
Okay. So, okay. Okay.
I trade on the stock market.
Please never do that. Okay. So, thinking about the set of all possible experiments, almost all of them are completely bizarre, completely irrelevant, completely not worth your time. So running an experiment takes time and energy and money, and you need to be able to set aside almost all of them and just run a few. Yeah. Just a very tiny number of the possible experiments. And paradigms are what help sort of narrow that down for us. They say, here are the sensible experiments. Here are the experiments that are worth running. Now, that excludes some of the experiments that actually will turn out to have been worthwhile. That's the catch here. Yeah? So we can't know ahead of time. So here's the problem with narrowing down your field of view. You can't know ahead of time what the good experiments are. You don't really know until you tried them, right? So this is the trade-off of paradigms. I'm really not recommending that anybody try to do science outside of a paradigm. That would be really unhelpful. So don't just start doing experiments at random. That's a bad strategy. Also why science fairs are terrible, because they're just like, try an experiment at random, see what happens. That's not how any of this works. But on the other hand, the kind of experiments that you run, the chances that the paradigm has caught exactly and only the useful experiments, the experiments that would reveal something interesting and important about the world, seems vanishingly low. We're not done this thing yet, right? We haven't got it all figured out yet. So the chances that your paradigm has just got everything that's important about the universe is almost zero. So we're kind of in this bind, right? We're kind of in this trap where, the paradigm has to be there in order to focus us, get us all on the same page, get us all pulling in the same direction, but it's also constraining us. It's also excluding things that are probably going to be important. Yeah? So, and that's, again, I think that's not just science. I think that's very general. It's a very general fact about human cognition. So, like, every time we come to the world, we're interpreting it through some framework or other. Right? You don't come to the world just raw without some set of assumptions and beliefs about what it is you're seeing. You can't, because there's way too much of it. You need constraints. You need models. You need to approach the world through some theoretical framework in order to make sense of it at all. The philosophers in the room, this is Kant's basic point. Yeah, like Kant was saying this a couple hundred years ago. Like you don't just sort of stick your brain into the world and have it absorb data. You have an interpretive framework through which you're seeing the world. I used this example on the very first day. So I would suggest to you that Copernicus and Ptolemy, so Ptolemy had a model of the solar system in which the Earth was in the center and everything goes around us. So for him, the Earth is sitting still. The stars are going around. And when he looked up at the night sky, or the day sky, when you see the sun going around, it really looks like the sun's moving, doesn't it? It really looks that way. And even though we've all been raised with the sun-centered model of the solar system, you kind of have to work to get your brain to interpret it as, oh, no, the Earth is spinning around and around, and the sun is staying relatively still. Yeah? So in some sense, they were having different, after we figured out that the sun is at the center of this thing, we're having different experiences of the world because we're bringing different interpretive frameworks to bear on it. And this is why we can't be the first type of umpire, right? You can't be the first type of umpire who's just seeing not from a perspective. It's always from some perspective, and the perspective that you bring to bear will affect the experience, in some sense constitutes the experience that you're having. So there's no theory, for this is sometimes called the theory-ladenness of data. There is no data without some theoretical framework. That's the claim. No? There is no observation without theory. The theory tells you what you're observing in as simple a way, as direct a way as like looking at the stars and deciding whether they're moving or you're moving. The Copernicus and Ptolemy example is very dramatic, but let's get a little more specific about kind of modern scientific practice, shall we? Because this question of interpreting the world is not just a paradigm shifty geocentrism to heliocentrism sort of deal. It's part of the everyday questions of science. So like, when you got some data set, how do you interpret that data? And the fact is that there are a whole bunch of decisions to be made. I find this graph very, does this graph bother anybody else? It bothers the heck out of me. How dare you draw a straight line through those dots? That's horrifying. I hate it. Now, does that make it wrong? So I have an emotional reaction to this. Does that make it incorrect to have drawn a linear sort of summation of those points? Yeah.
It would depend on what you're modeling.
Yeah.
So there could be a situation where
right.
it would be appropriate to do a linear regression.
Right. Right. So it matters a lot, like, why are these dots below the line? Why are these dots above the line? It matters a lot what you're modeling. It matters why you're modeling it. It matters what science you're in. How close to the line do the dots have to be? All of that is relevant to deciding how you're going to fit the curve. So curve fitting is the question. So how do you fit the curve? How precisely should the curve match the data? You might say exactly precisely, 100% precisely. So the curve should pass through every single point. But that's not the right answer, right? That can't be the right answer because you get what's called overfitting. If you make the curve complex enough to pass through every single data point, it becomes less and less likely to predict the next data point, right? So there's some choices to be made here, and there's really no answer from heaven that tells us what the correct answer is. You figure out what the correct answer was after you know, like in retrospect, you know what the correct answer was, but not before. Not as you're in the process of trying to figure something out. So these choices have to be made. They're made mostly on the basis of some paradigm or other. Some set of accepted practices within a discipline, sometimes within like a sub discipline. This is how we do it in the molecular biology of the liver. And they've got standards and practices that are not shared with the rest of molecular biology, never mind the rest of biology, never mind the rest of science. So these kind of choices are not arbitrary, but they're not objective in the sense that there's just one clear right answer that everybody should always agree to. Let me develop an example. Here's an example of statistical significance, the p-value. Everybody heard of p-values? Anybody in the sciences will have heard of p-values for sure. Now, p-values have taken on titanic importance in the practice of science, and a lot of people are really worried about that actually, because it's not obvious that they should have the significance that they do have. But if your study does not have a certain p-value, then it doesn't get published. If your p-value is not less than 0.05, you don't get published. So that's an extremely important measure. Notice there's no corresponding, is there a corresponding effect size that you have to hit? No. Nope, not as far as I know. So statistical significance, p-values, is a measurement of how roughly, I'm sorry, I'm going to do this roughly because I'm not like a scientist myself, but like how likely it is that a result is just due to chance. Yeah? How likely is it that So given some statistic, some model of the scenario, you got a model of a data and you've got a set of data, you can calculate how likely it is that that set of data is just a random occurrence or whether it's a result of some causal influence that your hypothesis posits. Yeah? So the smaller the p-value, the more unlikely it is just random chance, the more kind of confident you should be that you come up with something that's real. So p-value. Now, so as I said, there's this, so p-value of 0.05 is the kind of accepted gold standard, right? So let me tell you how that got introduced to the kind of statistical methods, if you haven't heard this. So this is from R. Fisher's book, 1935 book, The Design of Experiments. Fisher's one of the big names in thinking about statistics. He's also a huge influence on population genetics. He's one of the people that sort of pioneered the field of population genetics, so he's like a huge figure. And in 1919, he was working at a research institute in Britain. This is how, okay, so here's a fun little story. And this is reported in Fisher's book. It's kind of big incident in the kind of history of designing studies. So it happened one afternoon when he drew a cup of tea from the urn and offered it to the lady beside him, Dr. B. Muriel Bristol, an algologist, one who studies algae. She declined it, stating that she preferred a cup into which the milk had been poured first. Nonsense, replied Fisher, smiling. Surely it makes no difference. But she maintained with emphasis that of course it did. From just behind, a voice suggested, let's test her. So I don't know if you know Brits and their tea. They care a lot about whether you pour the milk in first or whether you pour the tea in first. And Fisher was having none of this. He was like, there's no way you can tell the difference between tea poured in first or milk poured in first. I don't believe you. And Dr. Muriel Bristol was like, yeah, I can. I'm telling you I can. So they set up this experiment to see whether she could. So make 8 cups of tea, 4 of which milk is poured in first, 4 of which tea is poured in first. Randomize them, yeah, and then present them to the good doctor and see if she can tell which is which. Okay, so there's only 2 conditions here. There's only 2 situations, either tea first or milk first. So if she was just guessing, she got a 50-50 chance on each one of getting it right, right? Now, her chance of getting identifying 4 out of the 4 cups that were prepared in her preferred way is something like 1 out of 70 or 1.4%. If she only gets 3 out of 4, the chances are something like 24%, something like that. So when they're setting this up, Fisher's madly doing all the calculations, just going to figure out, okay, how many does she need to guess correctly for me to be confident that she can actually tell the difference between tea prepared one way or the other. So, by the way, she identified 8 out of 8 cups correctly. So she was 100% of the time able to tell the difference between tea prepared one way and tea prepared the other. So she absolutely proved her case really beyond a shadow of a doubt that she could tell the difference. Yeah? Okay. So famous scientist disbelieves woman is proved wrong. So Fisher's the one, and this is part of the story. Notice that this cutoff between identifying 4 out of 4 and identifying 3 out of 4, 5% is sort of between there. Yeah? So there's a 5% chance. This is the p is less than 0.05. That is, there is the probability of her just guessing correctly by chance is well less than 5%. Do you know why he chose that specific value? Literally no reason. No reason. He just chose a value. In the original paper, he's like, yeah, we could do 5% or 2% or 1%, whatever you want. And people latched on to the 5%, or the less than 0.05. So this is an actually arbitrary choice. I know I've been saying before, like, it's not really arbitrary. This is an actually arbitrary choice about what counts as statistically significant that turns out to have really big impacts on what gets published. Because if your p-value is more than this value, you don't get published. If it's less than that value, you get published. So it's an actually arbitrary choice. And this is not just sort of me as a philosopher outside science critiquing scientists. Scientists are very worried about this. They're talking amongst themselves about like, why are we doing this? So there might be we might see in the next, so as I've been saying, the scientific method is a kind of myth. Scientific methods are constantly under revision. If I was a betting man, I would bet that in the next 10, 20 years, this will become much less important as a strict cutoff. People are onto this scam, right? People are onto the idea that this is an arbitrary cutoff of no objective significance. Nonetheless, here's a fun study. So here's a study on what's called p-hacking. So p-hacking is making choices about which data to include and which data to exclude, which methods of analyzing that data you use, how much data to collect. So you can, for example, just once you get a p-value of less than 0.5, you can just stop doing your experiments, right? So there's a whole variety of ways under the title p-hacking to subtly influence, without actually lying about anything, the p-value that you get. This group of researchers did a kind of meta-study. They randomly selected 575 p-values from medical studies. And notice this curious spike just at 0.05. Very curious. Weird, isn't it? That so many studies got just exactly the amount of statistical significance that you need to get published. Weird, right? Now, this is on p-values for their primary object of study. They compare this to secondary objects of study. So sometimes you run a study looking at one variable, and then you also do a sort of side project on another variable. I didn't include that graph, but that graph is mostly flat. There's no big spike at 0.05. The primary values are the ones that either get you published or not. The primary values, weird that there's this huge spike just at the point arbitrarily chosen by a man who didn't believe his colleague could tell what kind of tea she was drinking, decided was the cutoff for statistical significance. Like if he'd prepared 12 cups of tea rather than 8, this number would have been different. It probably depended on how many mugs they had available. Literally, that's how this got decided. Weird, right? So this is taken to be evidence, this study takes it to be evidence of what's called p-hacking. Now, are these people producing bad science? That's not clear, right? That's not the conclusion of this study. It's not that they're being dishonest. It's not that they're producing valuable knowledge that's not valuable. Because this is an arbitrary value that they're trying to satisfy, right? This 0.05 statistical p-value doesn't matter all that much. So it's not obvious to me that it matters all that much whether they fudge things a little to get just below that value. But notice how there are choices to be made in what we decide counts as significant, and that those choices affect the way scientific results are reported. These choices actually affect the way science goes. Yeah? So, there's a broad concern about this, and believe me, I'm not like the guy to figure this out. I'm reporting to you what a really wide group of scientists are sort of self-criticizing about. So this is not evidence that science isn't working, actually. This paper is evidence that science is working the way it intends, which is a self-improving process, a self-criticizing process, a process which tries to get better over time. So that's why the illusion of one single well-established scientific method is so dangerous, because that precludes exactly what they're trying to do here, which is to reflect and improve on the kind of methods that we find acceptable, the kind of methods that we regard as reliable. Right? So since 1935 or so, people have regarded this specific p-value as the cutoff for what matters. And now people are being like, well, is that appropriate? Is that the cutoff that we care about? Is there some deeper and more interesting way of analyzing this data? What methods of analyzing data are the right methods? And there's a kind of feedback process here. There's a kind of self-critical, self-improving, self-reflective, ongoing process of trying to get better and better at this stuff. And if you had to pick something out as essential to science, as the kind of juicy innards of science, I'd say that's it. The fact that they're not satisfied with methods, the fact that there is not the scientific method, but a kind of continuously evolving and developing collection of methods. Okay. So I think we should be careful to distinguish between at least three things, even if there's sometimes going to be sort of fuzzy boundaries between them. So these are three things that are, I think, in essence different, but there might be some gray areas. The choices that we're making, like the choice of what counts as statistically significant, ideological delusions that are imposed on us by our assumptions and beliefs about the world, and just straight up fraud. And all three of these things exist in science. I think I'm going to try to give you some examples of all three of them, but we should nonetheless keep them separate in our minds. Yeah? Okay, so I gave you some examples of choices. So that story about the statistical significance and the p-hacking, that's about the choices that we make about what counts as a good way of analyzing data, what counts as a significant result. Let's talk a little bit about ideological delusions. So everyone has some set of assumptions that they make about the world. Let's call those assumptions, and those assumptions are often unconscious. We're not aware that we're making them. So let's use the word for the purposes of this class, let's agree to use the word ideology in the following way. Assumptions that you're not aware of. Yeah? Students often use the word ideology synonymously with idea, which is, it's like nails on a chalkboard to me, but it's too useful of a word in this more sophisticated sense to give up on. So assumptions that you're not aware of, right? Things that look to you like they're facts about the world, but are actually facts about your belief structure. Let's call that ideology. You can't get through life without making assumptions. You just can't. There's too much of it. It's too complicated. So I'm not recommending we give up on assumptions, but we do want to be sort of aware of them and aware of how they can structure the way we see things. Because sometimes these assumptions can genuinely distort and compromise the scientific process. They can just make us come up with the wrong answer. Let me do a couple of quick examples. We'll talk more about this when we talk about credibility. So here's one. This is not a this is one that was sort of widely accepted in the scientific community, but here's a medical diagnosis, drapetomania. So in 1850, this guy from the southern US, Samuel Cartwright, suggested that the desire of African slaves to escape bondage was a kind of mental illness. He diagnosed them with drapetomania, the irrational desire to not be a slave anymore. So this is, I hope you can see a pretty obvious example of somebody taking their values and ideology and treating them as though they were facts about the world. Yeah? Even at the time, even in 1850, anybody in the northern US even was like, that's ridiculous. That's not a mental illness, that's being a human being. So even at the time, this was not, I mean, it was reprinted pretty widely in the southern US. They were like, yeah, that's a thing. I've noticed that my slaves have that too. In the north, they're like, that's horrible. So it's a pretty, in this case, regionally specific ideological distortion, but here's a classic example. Now, of course, we'd never do anything like that in the 20th century. Oh wait, we did. So the Diagnostic and Statistical Manual, which is a kind of like psychiatry's picture of the taxonomy of various mental disorders, until the early 1970s classified homosexuality as a mental disorder. It was a disease, according to this sort of like very official, very central collection of analyses of diseases. To be fair, it did come, I mean, homosexuality was strongly correlated with mental distress back when it was considered a disease, but that might be more correlation than causation. Yeah. So this was, again, something that was so obvious to people that there's a good and normal and a bad and deviant, that this is a disease. It wasn't actually, so this wasn't actually overthrown by any kind of scientific reflection. This was changed because people started storming into their meetings and yelling at them. Activists started like crashing the meetings of the Psychiatric Association, being like, "You guys are monsters." And to their credit, they were like, "Oh yeah, we are monsters." That's it could have gone another way, but yeah, they did eventually sort of change this, basically because of political pressure. Now, you might be, I'm 100% against classifying homosexuality as a mental disorder. I'm a little uneasy about people gate crashing scientific conventions and yelling at people until they change the science. But should I be? Like, in this case, I'm happy with the outcome here. Kind of wish it had come from within the science. I don't know. Thoughts? Yeah.
Well, I feel like kind of how you're saying, like, you can't really have, like, all science is coming from a certain perspective, and we have to consider the perspective.
Yeah.
Science is also, like, influenced by politics, and, like,
Yeah.
like, kind of how we were talking about, like, the other class, how, like, certain studies are chosen due to political pressure and stuff like that. So, like, even though, yeah, it sucks that, like, activists have to be like, hey, FYI.
We're not sick.
It's crazy. Like, it's
Yeah.
not crazy.
Yeah.
It still is like, it's just politics influencing science, but in like a way that isn't normally done.
Right, right. So maybe what we're seeing, thank you, that's good. Maybe what we're seeing here is, so science is influencing politics here. So the science itself is not value neutral. They're deciding this is a good way of being and this is a bad way of being. So they're sort of imposing value structure on the world. Maybe it's not that unfair that the world should kick back a little and say, no, your value structure needs to change. Yeah? Yeah.
I would argue though that there was no scientific evidence that was correct in the first place. Like, it never really was science anyway.
Right, right.
Like,
So here's the, I mean, for mental disorders in particular, here's the question, like, this is where the theory and the kind of constitutes the data. In some sense, you don't need evidence for your classification scheme. Like, you just decide what is and isn't a mental disorder. That's a kind of decision, it's in some sense an arbitrary choice. And then the sciencey bit is when you compare your choices, you say like, okay, now I'm gonna decide how to categorize the world. That's the framework through which I'm seeing the world. And then the sciencey bit is when you use that framework to think about the world. And like, I don't think it's possible to just not have the values, the categorization scheme. It's not possible to have that categorization scheme be completely value neutral. In fact, I'm happy that this isn't a mental disorder because I have some values that are informing my choices. I think homosexuality is fine, and that's part of my value structure. And I'm like, yeah, no, I'm going to impose my value structure on your sciencey thing. I want you to see your sciencey thing through my value structure. And I'm pretty comfortable with that. But like, I'm not going to pretend that my values are the result of science exactly. Yeah.
Well, okay, so as far as I know, protesting scientific conventions is fairly rare.
It does happen.
So in the cases where it does happen, that would be an indicator that something could be wrong. So that maybe it would make sense to like incorporate that into the scientific method.
Yeah, okay. Here's another thing that happens. Scientologists love to do this.
Oh.
They love to go around to psychiatric conventions and make noise at them.
Okay.
I
see.
I'm not hyped on that.
I see what you mean, yeah.
So, yeah. Oh, there's two of you with hands up, so fight amongst yourselves about who gets first. Okay.
I was going to say this is kind of a unique case because with mental disorders, it's something
Right.
that you see a lot.
Right.
Is things are only disorders or considered disorderly in the context, within certain contexts.
Yeah.
Like, for example, this would have been considered a disorder because it would have been, disorderly conduct within that society, especially
Right.
in a time when you wanted people to just keep on reproducing because babies died all the time. Or you see the same
Sure.
thing, you see kids that get diagnosed with learning disabilities because they can't do well in a classroom, but then when they get doing something with their hands or doing something creatively, they're brilliant. And so we're still like working on that, and I guess it would be the same
Yeah.
sort of in the sense of
Yeah.
the context for other things too.
Right. So an even more I think you were alluding to an even more modern version of this, which is ADHD, and we could do the same thing with ADHD. We could do the same thing with autism. These are being diagnosed as disorders, but they might just be alternative ways of being. Certainly, the autism community says, "Please stop trying to quote unquote cure us. We're fine. We're just different than you."
And there's a lot of theories out there that certain types of people in a variety of different ways of thinking, and the odd person who thought differently was actually beneficial in old societies.
Yeah. Okay.
Yeah, I was just going to add to that. I was essentially thinking that it's as we talked about earlier with framing the problem. At the time, they were trying to call things mental disorders, and there still are calling things mental disorders. And to add to what she said, it's essentially the difficulty is we're not really sure anymore if we want to call everybody out for having a disorder just because they show signs that indicate things. So it's like, do you want to call it disorderly just because they are obsessive in some ways, compulsive in some ways? You call that OCD. It's just a variety. It's a very clear variety of different things that come in people.
Right. So that's why I picked these. So that's right. So that's why I picked these examples. I think you're both quite right that this is probably one of the most acute cases of the interaction between values and science. So we call something a disorder. I mean, mostly the diagnostic statistical manual, almost every diagnosis in there now includes that it causes the person themselves distress. So it's got to be a problem for the person. But
Maybe that's kind of a bit of a social problem now.
Yeah.
And especially when it's like, oh my god, all of a sudden all of these young people have all of this depression and anxiety. I mean, the virus bootstraps or whatever.
Right.
Maybe there's something bigger at play.
Yeah. So this is supposed to be just an example of the sort of, the ways in which our assumptions and beliefs about what's a good society and how people should behave and all that stuff seems to have an influence on the way that we classify the world, the way we evaluate stuff. I mean, this is a pretty, I picked this case special. I think there's relatively little of this in particle physics. I don't know how, there's not a lot of people kicking down the doors at
Geology convention.
Yeah, not as much. A little bit because they do a lot of oil exploitation stuff, but there's lots of parts of science where nobody's protesting them, and it's really unclear to me, at least, how values might play a role, except in some much broader sense of values. So this is the sort of normal social sense of values, here's how you should behave as a person. There are broader senses of values that I think are more pervasive in science, but they're less kind of social values and more what we might call epistemic values, the kind of things that we think are useful or important in ways of learning, something like that. Okay, let's keep going. So here's an example. We should also distinguish all this stuff from what we may call just straight up fraud. So like there actually is a non-negligible amount, you might even call it a significant amount, of people just cheating, just not playing the game fairly. I would like to introduce you to one of my favorite Twitter feeds, Dr. Elizabeth Bick. She does some really good work on detecting image manipulation is kind of her specialty, but she's sort of broadly more in the scientific integrity game. She's reported hundreds or thousands of papers for probably fraudulent data. And she does really good work. It's super interesting. She does super interesting sort of stuff. Let me show you the kind of things that she posted. Let me show you a screen cap from her Twitter feed. Okay, so here's some images from a study, and the study was investigating the effect on frankincense on various organ tissues. Now, each of these, so this is a untreated or treated with frankincense, untreated, treated with frankincense. This is the brain, the heart, the liver, and the kidney. And Dr. Bick looks at images like this and discovers some disturbing things in them. You might not see it unless you know the game that she plays, but once you know the game, it's pretty obvious. Two of these images are exactly the same image. Top left. Those are pixel for pixel identical images, and one of them is supposed to be treated, and one of them is supposed to be untreated. So the study reported this as part of their data, part of their experiment, that this thing was unexposed to frankincense and this thing was exposed to frankincense, but they're the same picture. So they're lying. They're cheating. This is fraudulent. This is sham science. Yeah? Like that's just cheating to present images that have been present images as though they're something that they're not. Yeah? The problem with peer review is that they review what you're telling them. They don't actually, when they do peer review, you send them the paper, right? And we talked about how the journal article is this super cleaned up version of the actual events that happen. When they do peer review, there's nobody wandering around your lab. There's nobody digging into your notebooks. There's nobody even looking at the original data that you use to do your analysis typically. They see the journal article that eventually gets published and say, does that sound right to me? And the whole prior part of the process is really taken on trust. And I think most of the time that trust is warranted. Because scientists, I mean, if you're looking to make a ton of money in the world, don't be a scientist. That's a terrible way to make money. If you're looking to just extract the most money that you can, money and fame are your goals, almost everybody goes and does something else.
Finance and investment banking.
That's one method. Yeah.
I just think it's interesting, like you say, like most science isn't like that. But now, like I'm in forensic science, and like most of forensic science is like that. Like most of it is like the big names, the fraudulent people who knew nothing. So it's like interesting to come to this course and like learn all these things. And you're like, oh god.
Yeah. There's some worry that we've been under-detecting this in other sciences. So the fact that they're teaching you this in your classes, I think is, once again, actually a really good sign. It's a sign of the health of your science because they're worried about it, they're talking about it, they're presenting it as a serious issue, which means they're trying at least to do something about it. Yeah? So that's how we get better. And again, I do not think that this is evidence that science doesn't work. I think it's evidence that science does work. This is a scientist trying to make science better. Right? We shouldn't despair when we see things like this. We should actually be encouraged because people are trying to do better. So Dr. Bick did a study with a couple other people who trying to estimate the prevalence of this stuff. When I say most science isn't like this, I actually mean most in a statistical sense, like the majority isn't. They took images from 20,000 papers, roughly, in 40 scientific journals from 1995 to 2014. About 3.8% of published papers contained what they call problematic figures, with at least half exhibiting features suggestive of deliberate manipulation. So things like, the thing in the green box here, so the colored boxes are added by Bick and collaborators. The thing in the green box is identical to the thing in this green box, blue box, blue box. And that's not the kind of thing, so she's classified these things into, yeah, maybe you just put in the wrong image and whoops. And another level up is like, that's hard to do by accident. Yeah, there's some Photoshop work in there. Somebody spent an afternoon in Photoshop messing with those images, yeah, to get those to be identical. So that's deliberate image manipulation. 3.8% is the one where you're like, oh, that shouldn't be like that. And she thought about half of them could plausibly be honest mistakes. And the other half were like, no, okay, you didn't accidentally make that image look like that. You did that on purpose. And that's just, again, so 3.8% is the figure that you get from, she's just looking at the published articles. She's literally just looking at them and being like, does that look like it's all made up? And in 3.8% of cases, she found that, yeah, there was at least one image where she could just see that that's not real. That's just the stuff that you can tell from looking at the journal article. If I was going to commit scientific fraud, I would do it in cleverer ways than this. I would like to say that I would do it in cleverer ways than like this, such that somebody looking at my journal article couldn't go like, ah, that's fraud, right? Like you could just look at this image and go, ah, that's fraud. I can tell from just looking at it. I would like to think that I would do better than that. I would be a better scientific fraudster. I mean, again, if you're looking for a grift, start a cult. I don't know. Do an MLM. I don't know. Something, there's way easier ways to scam people than this. But if you're going to be a scientific fraudster, at least do better. Come on, you're embarrassing us all. Come on, guys. Do better than this. I mean, we can talk about the kind of motivations people might have for this. It's hard to get grants. It is genuinely hard to get grants. And if you don't get grants, you don't get to be a scientist. So there could be some survivorship bias here, some kind of natural selection where the honest scientists don't get grants because they're doing studies that don't produce statistically significant results, and therefore they don't get to stay in the discipline. Whereas the people who do get to stay in the discipline are people who will do whatever it takes to stay in the discipline. So they might have started off honest and found that the only way to get to hang on is to cheat. These are deep and serious questions about the incentive structure in science, I think. That, again, to try to make this not so grim, people are talking about this stuff, at least. We're talking about how it's possible to deal with this stuff. We're talking about ways to detect it, ways to discourage it. Yeah. So we should keep in mind the differences between the kind of choices in data analysis that we make. What kind of curve fitting should we do here? The kind of stuff that happens because you're sort of blinded by ideology, and straight up fraud. Now, Grinnell's really not going to talk much about either the fraud bit. He doesn't really, I mean, that's not his topic. The choices and some of the delusion stuff. I mean, I think that there's these things kind of shade gradually into each other, yeah? Like the difference between making a choice that happens to get your study below 0.05 p-value and doing fraud is maybe pretty gray. And similarly, the difference between being blinded by your viewpoint and actually cheating, that might be unclear sometimes what actually is happening. But Grinnell's much more on the choices end of the spectrum. He wants to have us think about how honest scientists doing science as well as they know how can nonetheless have values and interests and passions play a role in the best of science. It can nonetheless play a role in the best of science, the good stuff, the stuff that's, I don't know, funded well enough that you don't have to lie to people to keep on keeping on, that kind of thing. And he doesn't think, he's going to try to make the case that in the best of science, the role of values is not necessarily destructive. That is, caring about what you're studying doesn't make you a bad scientist, and it doesn't make what you're saying wrong. Caring about what you do is actually part of the process. In some sense, I would like to make the case, we see by caring, right? You constitute a world for yourself by caring about it. That's part of perception and cognition, is giving a crap about what's going on around you. So that's true of thinking in general, I would argue. Grinnell's going to make the case that it's true about science in particular. We're going to mostly leave delusions and fraud aside because we would like to talk about the best case scenario, and this stuff is kind of depressing. If we're going to, harping on about it is not what I'm after here. We're really not trying to cast doubt on the scientific process. We're just trying to complexify and enrich our picture of it. Something like that. Yeah? So, yeah. So Grinnell contrasts, this is all taken direct quotes from his book, contrasts what he calls the classical view, we'll be calling the linear view, with what he wants to replace it with, which is the ambiguous view. So we state the problem to be studied. Grinnell points out that choosing a problem commits you time, money, energy, and getting it wrong can derail your career. We carry out the experiment, and Grinnell wants to develop this idea that, what's important might not even be noticed, and what counts for data one day might be just noise the next. I'm going to go through these one by one, so we'll come back to all this. In the classical view, observations sort of straightforwardly confirm or falsify your ideas. In the ambiguous view, if the results don't meet your expectations, it might be because you didn't set up the experiment right. Hence the adage, he says, don't give up on a good idea just because the data don't fit. And he's not talking about fraud, he's talking about serious, honest scientists. And he thinks that this is true. Like sometimes you just got to keep hammering away at it until you get an experiment that works. And of course, we seek verification by other researchers of the findings and conclusions. And unfortunately, discovery claims are often greeted with skepticism or disbelief, especially when they're very novel or unexpected. Often scientists have to advocate for what they're talking about. So let me just quickly go through some examples of each of these, like choosing a problem. We've talked about these questions already. So like what gets studied and how hard does it get studied? We talked about mental illness. The question of what pills improve mental illness has been studied really, really hard. The question of which social programs improve mental illness, not so much. There's a lot less money for that question. Or like, how do we organize society such that people are happy? Very little study on that relative to what drugs do we put in their mouth to make them happy. And the money is the real question. How do grants get distributed? And this is a really complicated negotiation between individual scientists, institutions like universities, governments from whom most of the money ultimately comes. There's a whole constellation of university, government, corporation collaborations that drive a lot of research these days. So it's a very complex story about who gets money, how, and why. Okay. I'm going to skim over this stuff because we're running out of time. Does anybody know this fun story? So Pfizer was testing a drug called sildenafil to try to treat heart pain. And it didn't really work that well. for heart pain. Okay. But it turned out to be very effective at another condition. It is marketed today as Viagra. You might be familiar with that one. It's Pfizer's blockbuster drug. So that's not what they were studying when they developed Viagra. They were studying how to treat heart or like chest pain. So this is a classic example of unexpected discovery, something that was, kind of noise, but somebody obviously cleverly said, this is an important finding, at least from the perspective of marketing drugs. This is a crucially important finding, right? It's one of their biggest sellers. So there's a whole bunch of examples like this, less funny examples from the history of science of somebody trying to do one experiment and then by accident discovering something else. X-rays, microwaves was like this. So the guy who invented the microwave was messing around with some equipment and found that a candy bar in his pocket melted. And it's like, oh, that's something. And then decided to investigate and develop the microwave. That kind of thing happens all the time. We already talked about this one, so don't give up on a good idea just because the data don't fit. We're talking about this sort of like discovery of DNA turning into RNA, being transcribed into RNA, being transcribed into proteins. And this is the Nobel Prize winner who did it, describing how they, full of energy and excitement, sure of the correctness of our hypothesis, we started our experiment over and over again, modifying it slightly, changing some technical detail, which again, it sounds like fraud unless you know what science is like. And now it sounds like, no, that's just how everybody does it. And that's how good science is done. Not by immediately giving up on hypothesis when the experiment doesn't spit out the right answer, but by passionately trying to show that you're right. Eventually giving up if the data comes out that you're wrong, but like, don't give up right away. Yeah. And finally, communicating results. Another fun one from the history of science. So for most of medical history, people thought ulcers were caused by stress, just like stress and too much acid in your stomach. It turns out they're mostly caused by a bacteria, or many ulcers at least are caused by H. pylori. And somebody figured this out, but couldn't convince anybody that he was right. So treating a whole bunch of ulcer patients, they would do a little biopsy on their stomach, and over again they'd find this bacteria, and could not convince medical science that this was the problem. So what he did was cooked up a flask of this bacteria, drank it himself, got an ulcer, gave himself antibiotics, cured himself. Because it wasn't ethical to do experiments on humans. You can't give people ulcers on purpose, right? You can give yourself ulcers on purpose. So this is a case he couldn't convince people that he was right until he did this fairly dramatic thing of like drinking a flask of bacteria, giving himself an ulcer on purpose. And then people are like, oh, okay. And he got a Nobel Prize too. So this is a pretty dramatic case of having to advocate for your results, right? Not just sort of putting it out there and hoping for the best, but actually trying to sell people on your ideas. Yeah? Okay. So once again, the basic picture that he's trying to convince us of. So next week, you're going to read chapter 2, and we're going to start in talking, sort of focusing in. Right now we've been doing the broad picture. We're going to focus in on the discovery process a little more carefully, and I'd like you to read chapter 2. Okay, that's it for today. Thanks, everyone.